Okay, then just to remember, the idea was to take our nanotubes and try to modify the interface. Okay, and to do that, I want to do on the surface of the nanotube different treatments. Okay, one is the oxidation, and I think this modeling is the best one to show you. Here we have our multi-walled carbon nanotubes with the different layers, and I want to incorporate here some elements through the oxidation, okay? Carbon, oxygen, and oxygen there, in order to modify this interface. Well, I will not go in detail, but check the literature and then different possible treatment in air, in basic, or with acid, different temperatures and times, and I measure what is the content of oxygen that at the end I incorporate. The problem, you can incorporate a lot of oxygen if you do treatments at really high temperature and for long times. But what happens? That then you start to degrade this layer and you degrade your nanotubes. Then it's a balance. You should oxidize or degrade a little bit your nanotubes, but with a control. And to do that, I use again this micro ramen. Okay, but just to keep in mind that finally we did is a mixture in acid nitric sulfuric acid at 80 degrees just at 4 hours, because we keep the integrity of our nanotubes, the value is quite similar, introducing a content of oxygen that we thought that was enough. Okay, then we select this one up the optimize. We characterize the peaks to be sure that we introduce these oxide elements by infrared, but was there. Okay. The other step that we did, the boron nitride coating. Unfortunately, we didn't have this chemical vapor deposition and this really nice technique that probably are much better to do it. But okay, that we did is to do it through a chemical reaction that is really cheap. Then, well, we start with the boric acid, put in suspension and heat to create the boria, and also with the urea produce ammonia, I think it's that one in English, and there from these two components they react also a high temperature, creating this boron nitride. Okay, we did all this reaction with our nanotubes, and here is a TEM images where here is our nanotube, and for example this part of here is the boron nitride. Okay. And also, well, we measure by XPS that boron nitride is there, and of course, well, it works, but well, the homogeneity of this layer probably is better with the vapor deposition, the chemical vapor deposition, but it works quite well, and the thickness was in the order that we want, between 3 and 5 nanometers. Okay. And the last one, we want to use silica as coating in our fibers, because well, this silica is also used as the sintering additive in the silicon nitride, and then we want to incorporate and to control the adhesion. And here again, there are several possibilities, but well, the facilities that we have is just by reaction, and then it's like a salt hell. We introduce our nanotubes with well, different components, we heat it, filter, washing, different treatments. But the important point is that finally we coat our nanotubes with silica, as you can see here. Here is in a TEM images, here is our nanotube, and it's totally encapsulated in a perfect core of silica. In that case, the thickness of the layer is more continued, but also is thicker. Okay, and well, we characterize that really we have silica, not other elements. Okay, because it's amorphous silica, and by X-ray diffraction you cannot see it. The same happens with the boron nitride. Okay, and then we did the same processing, but with these nanotubes that were coated. And when we measure the elastic modulus, well, we see here is the silicon nitride, like the plant specimen, this one without any treatment, and this one with the treatment, the oxide, the boron nitride, and the silica. It's a clearly increase because we modified the interface, but okay, it's still not enough by this decrease of the nanotube. But at least we have improved this adhesion. And well, here is because we measured by two different techniques, the indentation and by frequency, by vibration. But okay, the idea is that we improve, but the elastic modulus improve it, but not until the level of the monolithic material. However, the hardness, finally with that one, like now the adhesion is much better. We are a little bit only less of the hardness of the monolithic materials, are even in the fracture toughness. At the end, when the nanotubes are coated with the silica, we produce this increase. But this is like we talk, okay? We should say everything. We improve the fracture toughness, yeah, from 6.7 to 7. Okay, yes, great for a paper, but not for a reality. But don't worry, because this is only the solution al problem that we observe. That we really want is the tribological properties, okay? But, well, we observe the effect, is for that, and we try to solve, and we did it, okay? And here's an example of the nanotubes when they are functionalized and the adhesion with that. For example, I like this picture, or even that one. Here we see that our nanotubes, when they are oxidized, they are really keeping between this part of the silicon nitride and this one is a fracture surface. Here they are doing this bridging, okay, or even keeping some pieces of your material put together, or here doing the bridging, here with the boron nitride between one particle and the other. Then we improve that even when the final properties are not the best one. But here is that I want really to focus, okay, it's the tribological properties. The idea, and well, I should say thanks to Christian Fischer to give me this nice scheme from the KIT in Gasway, because we want to use this our material really in engines. I mean, and then we try really in one of them, and this is the scheme how it works. And the idea is to use our materials in that part of the engine. Okay, this is that we did in a collaboration with Casbah Institute for Technology, or KIT, that is called. First, of course, we did in a laboratory scale this test. But at the end, we did it in really engines, okay, in these components or these components. The problem here, if you use metals, is that there are a lot of wear, okay, and then they think that probably with ceramics work better, because that you have here is a really high pressure and the isooctane, okay, the fuel, the gasoline, okay. And first that we did is tribological properties. I think here in this university you have one equipment like that, no? That's right? For measuring the tribological properties? Well, whatever. That is based in that you have your material, okay? In that case, or silicon nitride with the nanotubes. You have a ball or counter body, and well, for this one is reciprocal ball. That you do is apply a pressure, freeze your material and analyze. And like for the engines, will be all the time isooctane or a welder. We put a few drops of isooctane, okay? And well, this is the conditions. High loads, 50, 120 nanometers with a frequency of 20 Hz. This movement, because it's a reciprocal movement, in just 5 millimeters. That means that during 1 hour, I think was the experiments that we did, is a total distance of 360 meters, and we control the relative humidity, because it was in Germany and the relative was, the humidity is also so high, then it should be controlled. And in that case at room temperature in the chamber, but of course where is the content, the temperature is so high, okay? And well, here is when the pressure is 50 newtons for our silicon nitride with the different contents of nanotubes, and as you see, well, there is a small decrease there. When the load is low, well, the improvement is not the best one. But when we go to really high pressure, that these kind of engines work at that we see is that the silicon nitride is high, and with our nanotubes are lower volume and also more contact with the 8C%. For example, you see there are not all these peaks. Here even I think it's easier to see. Here is the coefficient friction as a function of the content of our nanotubes. For 50 newtons, the improvement is small, But when we go to really high pressure, and that is these kind of engines, we observe a reduction of the 40% of the coefficient friction. That of course it's totally critical. Also, if we analyze both surfaces, maybe the resolution is not the best one, but here for the silicon nitride, you see this is called pull out of the material. Okay, it's like you remove the grains. Okay, and here everything is more smooth. I will show you now why. It's because the nanotubes are doing, like, it's called tribofilm, okay, and then it's protecting the surface. But here there is no pull out of the material, okay, and here it is. But of course, it's not only the coefficient friction important in tribological properties, it's also the wear that you produce, because your pieces, of course, will be degraded, and at the end, this is critical. And here is again the wear as a function of the content of nanotubes, and that we see for 50 newtons. Well, it decreases always with the content of nanotubes, and the reduction of the wear is up to 80%. I mean, this is quite good. I mean, because okay, here the wear, let's say, is maybe you can think that it's not so much, but we should think that, for example, in a car, it should work for several kilometers, okay, and then the improvement of 80%, it's quite hard. Also, you can see here that with the highest load, is for all of them, for 50, 100, 200 newtons, the reduction of the wear of all material, it's really great. But also it happens, and this is quite interesting, not only in all material, it happens in the other, in the counterbody, in this silicon nitride that was freezing, okay? That this is the wear of the ball, okay? For 50 newtons and 100 newtons, let's say it's not a real improvement in the other counterbody, but when the load is quite hard, there are a really big decrease with a 60%, okay? And then is, yeah, that these carbon nanotubes, because it's the only possibility, reduce the wear in both bodies, not only in our material, also in the counterbody, okay? And well, here just it's more technical about these values, then what does it mean, and well, is that it's not a severe wear, it's just a mid wear by micro abrasion that I can show you later. But well, the important thing is this reduction, that is quite hard. We are not talking now 20% of only one thing, it's about really in really experiments, okay? Well, again, this D and G peak of the micro Raman spectroscopy. Well, at least here you can see how they look like. Well, we use this to analyze what really happened with the nanotubes. Just keep it in mind, because we measure first after the polycene and in the center or at the edge of this wear scar. But that we observe is that, well, this is here that I put, if this value increase means more degradation, and is the idea, because of course you start to freezing, and obviously your nanotubes start to degrade. And this is exactly the idea that we want, is that these debris and these particles that are there are lubricating effect, that they have a lubricating effect. On the other hand, if it's only silicon nitride, they act as a abrasive material, okay, and then this is quite bad. And even it's possible, well, I think with this resolution it's not possible, but here, this is only analyzing the surface, you can see that the carbon nanotube survives until they have the moment that they start to freezing. Then it's a continuous lubrication of your material. They start to degrade, and all the time has this lubricious effect, okay? And obviously, it's more accumulated in the edge, because like you are moving like that, of course you move all your material, okay? And well, here a couple of pictures to show you, no? It's here we increase the content of the nanotubes, and here the low. This that I showed you at the beginning, okay? Silicon nitride maybe 50 newtons. Well, you see here that is like the crack, but if we increase the load, there are a lot of pull out, okay? A lot of cavities. However, if we increase the nanotubes, even here, for example, in the other extreme, we see that the material has not gaps or cracks, and you can say that's not true, because we see these cracks. Well, this crack is that I told you that is a tribofilm. This is not the material. This is the compaction of the degradation of the material. It degrades, it puts on on the surface of your material, doing like in the between the two bodies, is that it's called third body, and it's lubricated. Then it's passing, and of course through the pressure, it's like attached to your material, but it's not direct your silicon nitride. It is only the debris. However, here even you can see, mainly briefly, this slide. This is because the surface is not protected anymore. Okay. And yeah, well, here is what is the reason for this triple film that protects your surface, and also, well, by the macro mechanical properties that I think I will show you later, not by this hardness or toughness that we see that they doesn't increase. Also by the pressure of contact. I mean, there is for a lot of things, the pressure evolutes with the content of during the test, because of course you apply 50 newtons or 100 newtons, 200 newtons at the beginning, but of course depends the area. I mean, this is like a ski, and here even the pressure contact increase with the nanotubes even when it has a better response. I mean, this is a really good values. And also, well, the thermal conductivity that I will show you, they it is expected that the carbon nanotube dissipates the temperature, but this is not true. The thermal conductivity decreased. Then we cannot use why is this improvement, but I will show you now is this resistant to the contact damage. Okay. And to do that we did is, so it's typically done. You take your material, cut it, and do indentation, but instead with a tip, with a ball. Okay, and then we will analyze what happened here with the micro cracks that are always formed. Okay, then in that moment that you apply, well, I don't know if you remember, normally when you have a tip, the low is quite low, and here we apply 2000 newtons, that is so much. Okay, then it's important that you keep in mind we will analyze this surface of the monolithic and in the composites, and also that one that is critical. Okay, the contact damage. This experiment was a little bit more complex. Here is the surface, and here is the section. Okay, here the surface, and here the section. In the silicon nitride, this is the characteristic response with the classical cracks. Okay, this one is really bad for ceramics materials, and this response. However, with the nanotubes, even when we measure the fractal toughness and the hardness, and these values decrease, in the contact damage, we see that these cracks, okay, it happens, but also we'll see here a response. Okay, here I don't know if, well, yeah, it's here. We can observe here like a small micro cracks. Okay, that will decrease the energy that are passed through that one, and for that we use these specific lights, and also go to the CEM to see that in that area, that not here, that is without any cracks, all the energy is going down and then break the material. Here a lot of energy is dissipated in that area, okay, through the formation of these micro cracks that help, and you see here the nanotubes how are acting, okay, and this is why it's improved at least the damage contact. Okay. Well, and now, and I will try to be brief, I think so, with that one, is the electrical properties. Well, probably you know, but silicon nitride is a really insulator material. I mean, you want an insulator material, probably silicon nitride is one of the best. Then we are here, nothing. But with a really small amount of carbon nanotubes, just even less than 1 volume %, we increase a lot, and we have a threshold in conductivity. Okay, well, it's an increase of more than 13 orders of magnitude, of course, because it's a really insulator. But then this is quite interesting for electronical properties. Was not the objective of for material or the target, but okay, it's there, and then we characterize. Well, and we measure different temperature, how they react, like the semiconductor and so on. Also, I will show you later, I think we observe different mechanisms of the electrical conductivity. Okay, but why even this value is low? Because the nanotubes has a really amazing electrical conductivity. There are for two things: the nanotube contact. Okay, when they measure the electrical or the amazing properties of a graphene of a nanotube, is because they measure just one. Okay, great, but we want to use it in a material. Then there is contact, in that case nanotube or graphene, and there is a really large potential barrier. And also that well, our nanotube has defects and another thing that of course disturb the property values, okay? But well, also we measure where is the current by this technique, okay? But well, it's important that also we observe a small, really agglomerate. We are talking about 200 nanometers. I mean, this is not critical, but we observe different electrical properties depend where you measure. I mean, here we measure the characteristic semiconductor mechanism that correspond with these graphite domains separated by the defects, or others where it's the classical metallic one in the intensity voltage representation. That is correspond exactly with the nanotubes by itself. Okay. Well, we also measure here. We can see even our nanotubes. The matrix doesn't conduct. That is the silicon nitride, and here we see exactly the nanotubes, the diameter of the nanotubes, because this one correspond with that, and there is when we observe this metallic response. Okay, but yeah, the electrical properties was not the really important ones, but has a critical effect for this kind of materials. Okay, that is exactly that one, the application. Silicon nitride has amazing properties for high temperature, but one problem: if you want to mechanize a final piece, it's horrible. I mean, it's really hard and brittle. Well, brittle stuff for a ceramic, but in general it's brittle. It's really high, expensive to mechanize this material, and to obtain a final piece is quite hard. And you should cut it or de-grinding always with components that are coated with diamonds. Okay, it's so expensive. But then there is a technique that I don't know. I think is the next day. That is EDM, electrodischarge machining. That is quite cheap, is well used, and is a thermoelectric process that is relatively easy, or so easy, process this kind of materials. But what is the problem? That you need that your material is electrical conductor. Like silicon nitride is not electrical conductor, you cannot perform EDM. But what happened? That we incorporate the nanotubes, and then it is. And if we can use this technique, this problem that is really a big problem to go with the silicon nitride to the market is solved. It's a really good advance. Typically, even the companies, when they want to mechanize the silicon nitride, that they do is to add a 40 volume % of this titanium nitride. 40%. Okay. Well, this is the solution that they found. And well, just to mention, the minimal electrical conductivity that you need for this CDM is in these values. That is perfect because we overpass these values. Okay. Then we take our material, the classical disc for the SPS, and well, you should optimize the voltage that you apply in your EDM, but it can be processed easily. Silicon nitride, that is quite hard to do it in several hours and so on. In seconds you can perform these kind of things. And also, as you see, the accuracy and the roughness are quite good. I mean, the cut are perfect. It is 100 microns, and even if you go in detail, here the roughness is quite good. Okay. But it's not only that, because we compare then our material. Well, this was a collaboration with one Belgian group. We compare this is the material removal rate. Okay, the velocity that you remove your material, comparing our material with the material that use the companies, the silicon nitride containing titanium nitride. But then with our material, we even improve the velocity of this process in a 50%, and also because like you need a contract with the electrode to do these kind of components or tracks. This is the rate, the tool wear, okay, is relatively high for the titanium nitride, and we reduce the tool wear in a 70% with the introduction of the nanotubes. Okay, that is quite good. Also, the roughness is clearly improved. As you see here, the roughness after the processing, any processes is more required. You see here in the same scale, after our nanotubes, the surface is really smooth, and however with the titanium nitride could be great, but even it's worse than that one. Then, well, after a few experiments, 100 volt was the optimized because improves the material removal rate, reduce the relative tool wear, and the roughness is quite good because it's low. And then, okay, go to the next step, and we process a small piece to do an example. It's a question of seconds. Really a small piece is a gear that of course can be used in several applications. To perform that one in silicon nitride only is quite hard. You perform with the nanotubes is quite good for the companies. And then the next step is going already in the direction of the application, and then we tried in real engines in these parts. If you remember, this one exactly the 20 millimeters was great. This application looked as for us, and these 20 millimeters and also these kind of rings that can be processed but are more difficult, but exactly that one. And well, I think I have here not the results because then I gone and they do it, but that I heard it's a really nice results. And well, just the conclusion of the work, that was that we really process really homogeneous and dense silicon nitride with really high content of nanotubes. This is about the wettability of the SPS that for this presentation maybe has not many sense. Also, we improve the adhesion nanotube matrix to have this kind of reinforced effect and increase the mechanical properties. And well, through the addition of the nanotubes, we can perform this EDM that of course is critical through the addition or the improvement, of the electrical properties, and well, that at the end, finally, we can really perform short pieces with interest for the market. Yeah, and I think that's all. Only to remember that, well, obviously it was my work, but several people are involved for that from my Spanish group here in the Institute of Ceramic and Glass. Of course, Professor Johannes Schneider in KIT, and well, these people from Leuven, Oliver Malek, that did excellent work. Yeah, and now we finished. Thank you very much. And as usual, questions or whatever you want. Mm-hmm.
I believe that it's interesting because the properties don't improve.
Mm-hmm.
They don't improve that much when it comes to the nanotubes.
Mm-hmm. That why we don't incorporate more nanotubes, you mean? Okay. As always, depend the properties that you want. For example, if you are looking for mechanical properties, as you see, it's not any beneficial. For the tribological, I do something wrong. We see that at the end, I mean, you don't improve and improve and improve your properties. There are a limit, a threshold that is called, okay? For example, well, I do really bad. In terms of, come on. If you will add more nanotubes, even you will decrease your mechanical. But as I told you, it's not the idea. But for example, in tribological properties, okay, maybe it continues decreasing, but I don't think so. And well, one important thing is that nanotubes, here I show you, and looks like that it's quite easy to disperse nanotubes. Nanotubes are really complicated. Even, well, we had a problem, we buy these nanotubes for a company, commercial ones, perfect. The dispersion was great, was easy. We even asked the same company, and when they bring other nanotubes, we cannot disperse them. It changed from batch to batch, and then it's really complex. We try with other companies, and then we always observe bundles of nanotubes. Well, 8.0 volume percent of nanotubes is quite high. And also, even if you can do it, because for other methods we incorporate up to 20 volume percent, really well dispersed, there are different properties. For example, in that case, the thermal conductivity, it has not effect. I mean, once that you are past the limit, you can increase the second phase, but your properties will not really be affected. even can be in the other direction, because now then that you have maybe it's a nanotube matrix with silicon nitride inside. Okay, you should take care of that one, but of course you can incorporate until you see your thermal, depend the property. For example, here in the electrical, as you see, even with 5 volume percent, it's already the max, the maximal. You can add 8 or 20, but it's like that. You can incorporate, but it has no sense. Again, like always, it depends the properties, but in general, more than 10% is probably not required. Yeah, welcome. More questions, comments? No? Then, yeah. See you in, I don't know, 15 minutes, 20 minutes, as usual. Okay, then see you.